Alrighty. Minimize the maximum difference of pairs. You're given a zero index integer array nums and an integer p. Find p pairs of indices in nums. P pairs of indices. Nums such that the maximum difference between amongst all the pairs is minimized. The maximum difference among all the pairs is minimized. Also ensure that no index appears more than once amongst p pairs. Find comparison. Note that for a pair of elements with index I and j, the difference between a pair is nums I minus number j, where x, the absolute value of nums I minus nums j, where x, absolute value of x represents that value of x. Return the minimum maximum difference among all p pairs. We define a maximum of an empty set to be 0. So here, p is 2, so there has to be 2 pairs, and you want to find the lowest, you want to find the minimum maximum difference. So you want to find the second highest possible difference. So like maybe 10, 1, 7, 1, and this is 66. First pair is formed from indices 1 and 4. So 1 and 4 is 1 and 1. And the second one is formed from indices 2 and 5, so it's going to be 2 and 3. Oh, I see. So you want to find the second lowest, minimize the maximum difference. The second lowest difference. Here p is 1, so this is going to be 0. This is p is 2, then it'd be if this was 2, then you would minimize the maximum difference by doing 1, 2, and 4, 2. So if there was 2 pairs, so the difference is 1 and 2, so then the minimum maximum difference is 2. Let's test that. So if this was 2, this should return 2. Okay. And let's say I modify the first one, and maybe if this was 3, then what would happen? Go, probably go something like 1, 2, 1, 3, 7, 10. So it'd be 3 as the minimum maximum difference. I think. Okay. I think I understand what the output is giving. Minimize the maximum difference among p pairs. Okay. So let's quickly take a look here. Let's 10 to the 5th numbers. So it's definitely not, it's either linear or like n log n. It's probably n log n here. I feel like you probably want to do a sort. Probably want to sort the numbers. And then what? And then a simplified version would be pairing numbers that are adjacent on the sort? Would you ever pair numbers that are non-adjacent? Would you ever pair numbers that are non-adjacent? Let's see if I can come up with an example where the ideal, would you ever pair numbers that are not adjacent of sorted array for optimum for as part of solution? So for instance, right, if it was 3 things here out of 6 numbers, it's 1, 1, 2, 3, 7, 10. And yeah, so you would pair, no, I mean, I was thinking if you pair 1, 2 and 1, 3, but you could have paired 1, 1, 2, 3. That probably would be better too. So yeah. So right here you wouldn't pair something that's not adjacent. What if it was so you're guaranteed to be able to pair it using adjacent stuff. So I'm guessing you always pair adjacent stuff. Guessing you'd always pair adjacent stuff. 4, 1, 2, 2, 4. Yeah, you pair adjacent stuff there too. Okay, come on. When would it not make sense to pair adjacent stuff? I guess the other question is like, even if you did pair adjacent stuff, how do you know which adjacent stuff to pair to? So for instance, if it was like 1, 2, 400, 401, then you wouldn't want to pair 2 with the 400s, pair 400 with 401. Then how do you know, like maybe this is 4, this is 400, 410, and 411. In which case you would want to pair the 410 with 411. So either you're pairing the current one with the next one. What is number p? P is up to half. P is possibly using all the pairs that are possible. Possibly using all the pairs that are possible. So it probably wouldn't make sense to use a dynamic approach here. Dynamic programming approach. I was thinking like if you had like based on p how many free elements that are not paired would be, and then work around that. But I don't know if that makes sense for a huge number. You had like 1 or 2 that you're missing. Okay. What if you had 1,000 that you might be not pairing? For every number, it's either going to be pairing with the next number or the previous number in the sorted array. And you can't use a number twice. You might not have the ability to skip a number at all. So, like if there's P is 3 here, then you'd have to do 1, 2, 2 for 400, 410, 411. 1 with 2, 2 with 400, 410, 411, P is 3. If P is 2, then you probably just want to do like 2, 2, and 410, 411. I guess it doesn't matter, you could also do 1, 2, 410, 411. P being 10 to the 5th things, or P being half of 10 to the 5th things. For each number, determine the benefit, the difference in the benefit of pairing with the prior number, or the difference in the benefit of pairing it with the prior number or following number. So 400, you get 398. If you do 2 and 400, or you get 10 if you do 400 and 410. And then what? You say you prefer the 10 as the pairing difference. How do you know that one, like, you have enough freedom to do that, maybe, or forced to do the pairing that is 2, 400. If P is large enough, P is 3, then you have like no freedom there. And 2, now you know that if there was freedom, that was the best use of that freedom. So for instance, you could have used the 410 and the 411. If I were to do a binary search idea here, yeah, binary search idea, done that way. So I guess what the absolute value, what the minimum maximum difference is, and I just count the number of pairs that hit that. Okay, yep, I think this is it. Let's say is possible is going to be for a certain difference. Let's go ahead and maybe make this into what is Python's type for Boolean? Bool. Okay, bool. There we go. So the idea here would be, okay, binary search. I'm almost certain that this is going to be the approach. So in general, this is going to have a method which uses O of n time, linear time, to check if a certain value is correct or incorrect, and then do a binary search for that correct value over the space of n. If you think about searching for the correct value, in this case searching for the min-maximum difference, is similar to searching for similar to finding correct temperature in hot slash cold, in like too hot slash too cold game. So we're searching for the correct minimum maximum difference, and you kind of guess a certain number. In this case, you guess a minimum maximum difference that's possible to get, and if it's possible, then anything kind of above it is also possible, and if it's not possible, or if it's not possible, then anything above it is not possible. If it's possible, then anything below it is possible. So you kind of, if it's possible, then you can maybe guess higher, and if it's not possible, then you guess lower. But you have optimized guesses, so it's going to be kind of n log, it'd be log n to find the correct guess. But you just need to have a linear time, like a one pass method to check. And I think there should be a one pass method to check if it's possible to do some number of pairs. And that's going to be just a greedy approach, basically going through each. Here, this is pos function. We'll do one pass to determine if diff pairings are possible, or if not diff pairings, if p pairings are possible with certain difference, greedy approach. So for every pairing that has a difference that is less than this difference, less than or equals this difference, then I'll just increment it. And by the end, if it's less than or equals that, then that's a possible difference, or that difference is possible. So count is going to be 0 for every value in the sorted nums. I need indices, right? I need indices for every index in range n from 0 to n going up by 2. Fuck. I still need to want to be able to skip stuff if it's not, if there's an allowance for it. I do need to be able to skip stuff if there's an allowance for it. I guess I would automatically skip stuff if it didn't work, right? Yeah, I would automatically skip stuff if it didn't work. So how would I do this? So I'd say I think I actually want a non-for loop for this because for loops have those set indices that it iterates through. So for index equals 0 while index is less than n minus 1, if the value at this index, nums at this index, have the value of the nums minus nums at the next index, that is less than or equal to the difference in the count commits. And you want to skip over both those indices, else skip over this index as a possible starter index. Yeah, and then return whether or not count is greater than or equal to p. I wonder if I should have an if statement for the count here. If count is greater than or equal to p here, you just return true. Otherwise, return false at the end. You would make it slower. Yeah, it's probably still faster. If count is greater than or equal to p here, return true. Okay. And n needs to be defined. N equals length of nums. Below is going to be the low number would be 0 as the lowest possible difference. The high number is going to be, I guess, the first minus the last in the array. Is there a better way? Is there a better guess as to the high differences? First minus the last is always going to work. Nums of -1 minus nums of 0. And then for then have a while loop, so while low is less than high, the mid is low plus high divided by 2, and cost is possible for this difference, the mid difference here. If it is possible, then I generally separate out boolean from the if statement just in case I'm going to print it out. If possible, then I want to, if a certain minimum maximum difference is possible, then I want to try a lower minimum maximum difference. So the high needs to go lower. So something like mid equals high, else mid equals, or no, high equals mid. High equals mid, else low equals mid plus 1 is my guess about how this should go. If the low is equal to the high, then return that low. Okay, let's see if this works. I would probably be doing a little more logic about the edge cases here if I didn't have the ability to just run test cases. Alright. So p is 0. Okay, so if there's 0 pairings, the answer should be what? 0? The answer should be -1. What is the answer when p is 0? Yeah, we define the maximum after we set 0 to. So p is 0, then just return 0. Okay. So yeah, the reason why I'm pretty certain that this is, well, if you're going to sort the array, it's going to take n log n time. And if you do binary search method to find the optimal number, that doesn't increase that time frame. So that's why I thought immediately that this is valid. If it's not valid, if there's some faster way of doing this, then I wouldn't be able to sort at all. So either you can sort, and then therefore binary search is a possibility, or not. 117, that's a very low number compared to my speed. Okay, let's come up with maybe a faster. So low 0 would mean that they're all the same. So I think maybe the low could be 1 if they're not all the same. Okay, so I'd say yeah, I could maybe start the low as 1 if they're not all the same. And if they are all the same, then I would just return 0. So if p equals 0, or if what? Maybe here I can do 1, if I can do something where nums sorted, if nums of 0 equals nums of -1, then return 0. I can start with a low of 1. That might be slightly faster. Oh boy, it's not really correct. Interesting. So if I start this thing as a low of 1 and a high of 1, doesn't necessarily mean that. Interesting. Never mind. Yeah, it could always be low of 0 depending on the number of pairings because it doesn't necessarily use other numbers. Okay. Is there any other optimizations we could do? So count index 1, index less than -1, absolute value nums minus index nums plus 1. That is less than count increments. Yeah, the count of stuff is fine. If that count is at least p, turn true. Index plus c plus 2, otherwise index plus equals 1. And then otherwise, if you do the whole loop and you don't see enough pairs, turn false. This seems pretty optimized. I guess maybe this intermediate variable could be removed. So you could maybe do if is possible is removed. I guess that's one statement out of the loop. This doesn't seem faster, or it doesn't seem like it's significantly changed the result in terms of speed. Yeah. Did I optimize the high? Low should. Let's see how you can optimize the low. Optimizing the high instead of just assuming to check for the highest possible difference between the smallest and the largest. If you have p pairs, I think maybe it's possible to do the highest and lowest divided by the number of pairs. Because if they're all evenly spaced, then that's going to maximize their differences. Yeah. And if there is not evenly spaced, then it's actually going to, if it's not maximally spaced, actually, so does the answer decrease or increase if it's not evenly spaced? So let's say the first number is 1 and the last number is 400. So if it was 1, 1, then the answer is 0. 400, 400. The answer could be, so this is the high. Yeah, the high might be divided by p, maybe rounded up, but maybe just trying to divide by p. Yeah, so 4, 2, 1, 2. So here p is 2, 1, 2, 2, 4. I think I need to round up. 4 minus 1 is 3, divided by 2 is 1. Yeah, I need to round up. How do I do round up? Divide by p round. Python round. Does that give you an integer? Turn a floating point number that's the round version of the specified number. How do you do an int round? Round function is round to the nearest integer or specified number of decimal places. I thought the previous one said it was floating point. I'm going to say round works normally. I hope that's correct. Okay. Okay. So 670536. So 0, 3, 5, 6, 6, 7. 3 pairings. So it's just 0, 3, 5, 6, 6, 7. Maximum difference is 3. Okay, and I said the maximum difference was based on the spacing would be 2. Yeah, this formula just doesn't work. Theory incorrect. So I think it is in practice. Minus the last, minus the first. Yeah, it could be literally the biggest difference. So if it's like 0, 400, 400, 400, and there's 2 pairings, then it's going to be 400 is the maximum, and 400 is the answer. Or the minimum maximum, and yeah. So how do I improve this? Like this seems very optimal. Maybe if I didn't have variable for mid. That seems so quick though. This difference thing seems quick too. Guess maybe if I had an array of the difference, I wouldn't have to calculate it new each time. If I were to pre-calculate my difference array. So let's say diffs is this, and for every index, I'm going to do this after I sort. For every index in range n, for every difference in range n minus 1, diffs.append apps values nums index. Why am I doing absolute value here? I should just do the bigger numbers and small numbers since I know the bigger numbers are the little ones. So nums of index minus 1, index plus 1, minus nums of index. Okay, so I have a difference array. Pre-calculated. So I can just say here if the difference array at this index is less than difference, less than or equal to difference. Increment the counter, skip the indexes, check to see if it works as a necessary number of pairs. I think this is fine. Let's calculate. Yes. All right. I'll take it. So summary here. I mean, summary is kind of that comment, but in case people care and did not look at the other stuff, summary here is the binary search method. So first, ideal differences in that are used in pairings will always be found in using adjacent elements of sorted array to determine differences. So this algorithm, this sorting algorithm will be at least n log n, both n log n. Here we're going to so binary search method will have a single pass O and check method to see if a certain value for, in this case, the min max return value is valid, and use that method in a binary search, and use binary search to find the ideal, in this case the maximum, to find the ideal min-max value. Note in general, binary search is log n plus speed overall will still be O n log n. Like sorting is actually going to take longer than finding the correct value after that. And then here, so create a, so that single pass method, so create the check method, which will see if, which will be given a possible a maximum difference value, and see if p pairs of difference of adjacent elements in the sorted array has a difference less than or equal to that difference. Let's say maximum difference value d, maximum less than d. Return true if so, false otherwise. And then in the main method, use binary search to find optimum difference. So that was all this stuff. So this is possible. You have a counter for the number of pairings. You have an index that you're using for your pairings. Oh, I also note here, to cut down on calculations, create a difference array which stores the differences between adjacent elements in sorted array. So you have to calculate that more than once. Sorted array. cut down on redundant calculations. Okay, so anyways, the check method is gonna go through all the indices, check if the difference between the value of that index and the value of the next index is less than the difference that's been checked. If it is, then increments the count, goes to the indices that does include one of those two, which is the next two-way. Otherwise, it'll skip this one. This one will always work because, well, it doesn't really matter. Like, you can always be greedy with how you pair it up, because that's the only way that it would work anyways. And yeah, so if you can find any sort of pairing that works, it doesn't matter if it's like if you could pair this index with the index before or after it, as long as one of those things gets counted, then you just move on. You have to use a while loop here, because if you use a for loop, the index iterates through every single value, and you can't really skip indices easily in a for loop. Maybe with Java because there's less of a hard list of index values when you use a for loop in Java, but in for loops in Python, like if you use range, then indices can't be messed with. Okay, so you have your is possible, you have your this is basically your binary search method. You have a low value for your possible maximum and maximum difference, and you have a high value, which is in this case just the difference between your largest and smallest values in your sorted array. And then while you're still searching, while the search space is more than one, you find the mid value, and then you see if that mid value is possible. And if it is possible, then that means that, for instance, if the mid value is, let's say, 10, so you know that you can find some number of pairings where the maximum difference is 10, so you should try something lower. So maybe you try for like 5. So in which case the high point of your space that you're searching for becomes your mid. So now now you're trying for something lower. If your mid doesn't work, then that means that you need to try something higher because it's maybe not possible. So if you're trying for 10 and it's not possible to do 10, then maybe it is possible to do 20 or 50. So your low needs to increase. Okay, so once your space of searches down to something that's the same, then you search on the value. Time complexity is going to be O of n log n. To sort the array, and O of n to do the check, along with O of log n to find the optimum value. So overall it's going to be O of n log n. Like O of n times O of log n is going to be O of n log n as well. And then space complexity, this is going to be O of n to use the stored difference array. If you didn't do that, and I don't think you actually do need to do that, it's going to be possible to not use that, in which case it's O of 1, because at that point I think you need to store something.